Hey guys, welcome back to my channel. Um, this is another algorithm video, and today we're going to continue with the binary search and its case on the solution space rather than um, finding the maximum element or minimum element or whatever element from an array. So it's a usage of binary search in a more broader sense. Um, also, recently, I've also started another challenge alongside this challenge, which is learning Dutch. I don't want to talk a lot about it in this video because this is purely for algorithms, but I just wanted to tell you guys that um, this is the reason why I first started this channel. So I'm not gonna let it go until I finish the promised days. And I'm pretty sure I need to study and I want to study more uh, with the algorithms and doing projects with it, so on and so forth, or even contributing to open source challenge. Bunch of ideas. So yeah, it's just a start. I'm not stopping, so bear with me. Anyways, we'll go back to our binary search. Um, so we were talking about the solution space, and usually um, it is the case. I'm going to share my screen. It is the case that when we are trying to find the um, oh, is this share working or is it lagging? Guys, there was a bit of lag, but I'm gonna continue sharing my screen. Yes. So basically, it is the same as what we do on array. So um, we define the minimum possible element and maximum possible element in that kind of problem. Um, and we define the mid pointer as well. And then bit by bit, so we see if it's on the left side or right side of the mid pointer, and then we reduce and halve the search space, and then so on and so forth until we find that threshold where the solution becomes impossible to possible. So we are basically trying to find that point where um, point that will make this problem successful, the solution itself. So that's why we're gonna do that by trying out this question. It's called Koko eating bananas. So there's n pile of bananas, ith pile has piles I bananas, guards have gone and will come back in H hours, and H is given in the test case. Also, the number in the piles are given. Um, there's no significance in this list of piles. It's just that there is a significance, but there's not much to it. It's just the amount of bananas that Koko can eat. So it's nothing more, nothing less. Um, you don't even have to treat it individually, although it is easier if you do it individually. And the proposed output is 4 because Koko has to, um, 4 is the minimum eating speed, K, such that Koko can eat all the bananas within H hours. So in this case, that's 8. So in 8 hours, if Koko can eat 4 bananas per hour, then it will make sense. So that 4 is like the point where um, this solution, so the eating speed becomes impossible from impossible to possible. So before this 4, so if Coco was eating 3 bananas per hour, then this solution wouldn't have not work. So we'll just quickly see. I just drew all the try to visualize it. So this is a test case 1 where these are the numbers of piles 3, 6, 7, and 11, and um, the number of hours, the eating speed, the number of hours it takes is bananas divided by K, right? So because Coco can eat K bananas per hour. And I'm going to update this hour parameter here from the bananas divided by K each time it consumes the pile, so that I'll show you how it makes sense that when output as 4, so when K is 4, it can meet its constraint, which is 8 hours. So for instance, let's say that if K is 4, so 3 divided by 4 is 1, right? Because we have to round up. So we put 1 here, and then we move on to the next pile, which is 6. 6 divided by 4 is 1 point something, but we round up as well, so it's 2. Now we move on to the next pile, 7. 7 bananas divided by 4 is also 2, we round up. And then finally 11, it's 3, right? So we add 3. So if we add this all up, it becomes 4, 7, 8, right? So it just meets its constraint, which is 8 hours. If we have done this with K equals 3, so just before this, then we definitely know that it wouldn't have worked because, yeah, when we use K equals 4, it just worked. So implementation is pretty simple. We just follow the template that we have used yesterday. Um, just 1 second. It is important to memorize one of these templates. Let's see, where can we write our code? Yes. So if Coco eats K bananas per hour, the total hours required new total hours required to eat a pile of pile I bananas is um, pile I divided by A, right? So this is the total hours required, and this can be calculated using the K and pile. Now, the minimum possible value of K is 1, right? Because a Coco cannot eat 0 bananas per hour. It needs to eat at least 1 banana per hour. So this is the minimum. So we know that this is the left boundary. And what will be the maximum value that the Coco can eat? So that will be the maximum of the pile, right? So that will be, in this case, max of um, pile, right? So that will be the right pointer where the right pointer is pointing at. Now that we defined left and right, we use binary search process. So we use binary search to find the optimal K. For each candidate K, we calculate the total hours needed to eat all piles, and then adjust the search range based on whether the total hours exceed H or not. So that's why I said in the beginning, it doesn't really matter if you consider the pile individually or not, because we just have to calculate the total hour needed to eat all piles, right? So let's go into the code. We're gonna define a helper function here. I didn't solve this myself. I had to look at some solutions as well, but implementation, I did it myself. So let's define a helper function called can eat banana. Can eat banana and speed. Then when hours is 0, mm, can eat banana speed will check if Koko can eat all bananas at the given speed within H hours. And it would iterate through every pile and calculate the hours needed for each pile. And we're going to sum up all the hours. So that will be done by doing the iteration. So for pile in piles, um, hours plus the pile plus speed minus 1 divided by speed, right? Because here in pile I divided by k. And then we return, if the loop is done, we return hours h. Now, um, now we do the original binary search here. So left, right equals 1 max. The minimum is 1 max of pile, right? Piles. Now, while left is lesser than right, so if the left pointer is lesser than right, we define the mid pointer, which is left plus right divided by 2, right? And if this helper function here, can eat banana mid, if the mid pointer is there, then the right is mid, and if not, then left equals mid plus 1. So we initialize left to 1 and right to max piles. Then if the left is lesser than right, so we compute the midpoint of the current range, and we use the helper function up there to check if Koko can finish all the bananas at speed mid. And if she can, we reduce the search range by setting right to mid. So this is when the mid is the target. So if she can, and if not, we increase the search range by setting left to mid plus 1. And then at the end, we return the left. Let's see if this works. Hmm. Yes, so this works, guys. Um, it's just that we had to define a helper function separately here. But everything else was the same. We defined the left and right pointer. We checked if the midpoint is the target, or else we reduce the search range. So yeah, we're gonna do more applications of it in the upcoming days. So please bear with me. Binary search is nice because if you see the max and min elements, or this kind of question where we know that you have to find the threshold and the question is given you as an array, then we know that we can use the binary search, and it's pretty easy if you understand and remember the binary search template. So yeah. Anyways, that was it, guys. I need to wake up tomorrow early because I got a job interview. But yeah, thanks for listening. And if you guys have any comments, leave it down below.